At first glance, Lake Mead and Lake Powell appear to be enormous natural lakes, their blue waters winding through towering sandstone cliffs and deep desert canyons. From the air, they resemble inland seas carved by nature over countless millennia. In reality, neither lake existed a century ago. Both are artificial reservoirs, created when two of the largest dams ever built in the United States transformed the Colorado River into a carefully managed water system. Lake Mead was formed after the completion of Hoover Dam in the 1930s, while Lake Powell began filling decades later behind Glen Canyon Dam. Together, they became the nation's largest water storage system, designed to capture water during wet years and release it during dry ones. Think of them as two gigantic savings accounts. During years when mountain snowpack is abundant and rivers flow strongly, excess water is stored behind the dams. During droughts, that stored water is gradually released, ensuring that cities can keep their taps running, farmers can continue irrigating their fields, and hydroelectric power stations can keep producing electricity even when nature provides less water than usual. That strategy worked remarkably well for generations. Today, the Colorado River stretches approximately 1,450 miles, or about 2,330 kilometers, from the Rocky Mountains of Colorado to the Gulf of California in Mexico. Along that journey, its water supports one of the largest and most productive regions in North America. More than 40 million people depend on the Colorado River system in some way. It supplies drinking water to major metropolitan areas including Las Vegas, Phoenix, Los Angeles, San Diego, Denver, Tucson, and numerous smaller communities throughout the American Southwest. The river also fuels one of the world's most productive agricultural regions. Water stored in Lake Mead and Lake Powell helps irrigate millions of acres or millions of hectares of farmland that produce vegetables, fruits, grains, and livestock feed consumed across the United States and exported around the world. In many places, farming on this scale would simply not exist without the Colorado River. The reservoirs provide far more than drinking water and agriculture. Hoover Dam and Glen Canyon Dam generate hydroelectric power that helps supply electricity to millions of homes and businesses. Their steady releases also help regulate downstream river flows, reducing flood risks during wet years while maintaining water supplies during dry ones. The Colorado River is equally important for Native American tribes whose histories, cultures, and economies have been connected to the river for centuries. It supports recreation, tourism, fisheries, wildlife habitats, and ecosystems that depend on reliable flows through one of the driest landscapes in North America. Few rivers anywhere on Earth carry so many responsibilities. Every gallon, or about 3.8 litres, released from these reservoirs must satisfy a complex network of cities, farms, industries, tribal nations, power producers, wildlife habitats, interstate agreements, and international commitments extending into Mexico. Decisions made at Lake Mead and Lake Powell ripple hundreds of miles or hundreds of kilometres downstream, affecting millions of lives long after the water leaves the dams. That is why shrinking reservoir levels have become one of the most closely watched environmental stories in the United States. This is no longer simply a drought story. It is a story about the water security of an entire region. And that raises an even more important question. If these reservoirs are so essential to modern life, how did they lose so much water in the first place? The decline of Lake Mead and Lake Powell did not happen overnight. There was no single catastrophic event, no dam failure, no river that suddenly stopped flowing. Instead, the crisis unfolded so gradually that for decades it was almost invisible, hidden behind the vast size of the reservoirs themselves. To understand how the American West reached this point, we have to travel back more than a century. In the early 20th century, the Colorado River was both a blessing and a threat. Each spring, melting snow from the Rocky Mountains sent enormous volumes of water rushing downstream. In wet years, the river flooded farmland and communities. In dry years, it shrank dramatically, leaving settlements vulnerable to water shortages. Engineers and political leaders believed the solution was clear: control the river. That vision eventually led to the construction of Hoover Dam, completed in 1936, followed decades later by Glen Canyon Dam. Together they created Lake Mead and Lake Powell, two enormous reservoirs designed to store water during wet years and release it during dry years. But managing the river required more than building dams. In 1922, representatives from 7 western states negotiated what became known as the Colorado River Compact. The agreement divided the river's water between the upper basin and the lower basin, creating a legal framework that still governs much of the river today. The problem was not the idea of sharing the water. The problem was the river itself. The compact was negotiated during one of the wettest periods in the historical record. At the time, scientists had only a few decades of stream flow measurements and believed the Colorado River consistently carried far more water than we now know it usually does. Modern research using tree ring records has revealed a much longer history. By extending the river's record back for centuries, scientists discovered that the early 20th century was unusually wet compared with many other periods. In other words, the Colorado River had been allocated based on an exceptionally generous snapshot rather than its long-term average. For many years, the mismatch remained hidden. The reservoirs were full. Wet years compensated for dry ones. The system appeared to work exactly as intended. Meanwhile, the American Southwest experienced extraordinary growth. Cities expanded across the desert. Las Vegas transformed from a small railroad town into a global tourism destination. Phoenix became one of the fastest-growing metropolitan areas in the United States. Southern California continued to expand, while agriculture flourished across Arizona and California's irrigated valleys. As populations increased, so did demand for water. Every year, more homes, more businesses and more farmland relied on the same river. Then the climate began to shift. Beginning around the year 2000, the Colorado River basin entered what scientists now describe as a long-term megadrought, one of the driest periods in at least the past 12 centuries. Winter snowpack became more variable. Hotter temperatures increased evaporation from reservoirs, soils and vegetation. Snow melted earlier in the spring, leaving more time for water to evaporate before reaching rivers and reservoirs. Even when precipitation remained near average in some years, less of it ultimately became usable runoff. Hydrologists refer to this as declining runoff efficiency. A warmer atmosphere demands more moisture, and the landscape itself consumes a larger share of the water before it can flow into the Colorado River. The result was a slow but relentless imbalance. Year after year, more water left the system than entered it. At first, the declines seemed manageable, a few feet or about 1 meter one year, a few more the next. But over 2 decades, those small losses accumulated into one of the largest water deficits in modern American history. By the summer of 2026, Lake Mead and Lake Powell together held only about 14 million acre-feet, or about 17.3 cubic kilometers of water. When completely full, the two reservoirs can store approximately 51 million acre-feet, or about 62.9 cubic kilometers. That means they were missing nearly 37 million acre-feet, or about 45.6 cubic kilometers of water, enough to supply many millions of households for years. It is a staggering deficit, one that cannot be erased by an ordinary rainy season. Which brings us to an obvious question. If decades of drought created this crisis, could one of Earth's most powerful climate patterns begin to reverse it? Every few years, a powerful force begins to awaken thousands of miles or thousands of kilometers away in the tropical Pacific Ocean. It starts so quietly that it is almost impossible to notice without satellites, ocean buoys, and sophisticated climate models. The sea surface warms by only a few degrees, barely enough to feel if you were standing in the water. But across an ocean spanning thousands of miles or thousands of kilometers, those few degrees can reshape weather patterns around the world. That phenomenon is known as El Niño. To understand why it matters, we first need to understand how the Pacific Ocean normally behaves. Under ordinary conditions, persistent trade winds blow from east to west across the equatorial Pacific. These winds push warm surface water toward Indonesia and Australia, allowing colder, nutrient-rich water to rise along the western coast of South America in a process known as upwelling. This continuous circulation helps regulate weather patterns across much of the planet. But every few years, those trade winds begin to weaken. As they lose strength, warm water that had accumulated in the western Pacific slowly spreads eastward across the equator. Sea surface temperatures rise over an enormous area, releasing additional heat and moisture into the atmosphere. The Pacific Ocean effectively begins redistributing vast amounts of energy. That extra heat alters atmospheric circulation on a planetary scale. Storm tracks shift. Rainfall patterns change. Some regions experience severe drought, while others receive exceptional precipitation. One of the most important changes occurs high above North America. The subtropical jet stream, a fast-moving river of air several miles or several kilometers above Earth's surface, often shifts southward and becomes more active during El Niño winters. This altered jet stream guides a succession of Pacific storms toward the western United States, increasing the likelihood of widespread rain across California and heavy snowfall in portions of the Sierra Nevada and Rocky Mountains. These storms are often intensified by atmospheric rivers, long, narrow corridors of concentrated water vapor stretching across the Pacific Ocean. Sometimes described as rivers in the sky, atmospheric rivers can transport amounts of moisture comparable to the flow of some of Earth's largest terrestrial rivers. When these systems make landfall, they can deliver extraordinary rainfall to lower elevations and tremendous snowfall across mountain ranges. For the Colorado River Basin, that snowfall is especially important. Much of the river's water does not originate from rainfall over the desert. Instead, it begins as snow falling high in the Rocky Mountains during winter. That snow accumulates for months before gradually melting in spring and early summer, feeding streams and tributaries that eventually flow into Lake Powell and, farther downstream, Lake Mead. In many ways, the mountain snowpack functions as the basin's natural reservoir, long before water reaches the dams. The larger the snowpack, the greater the potential runoff. But not every El Niño is the same. Some events are relatively weak, producing only modest changes in global weather. Others become considerably stronger, increasing the probability of wetter conditions across parts of the American West, while still allowing for significant regional differences. Then there are the rare giants. Climate scientists often refer to the most exceptional events as Super El Niños. These are extraordinarily intense episodes during which sea surface temperatures across the central and eastern tropical Pacific become dramatically warmer than average, releasing enormous amounts of energy into Earth's climate system. Only a handful have occurred during the modern era. The Super El Niño of 1982 to 1983 caught much of the scientific community by surprise. It unleashed destructive storms across California, triggered widespread flooding, caused landslides, damaged infrastructure, and produced exceptional mountain snowfall throughout parts of the western United States. Around the world, weather patterns shifted dramatically, affecting agriculture, fisheries, and ecosystems across multiple continents. 15 years later, the Super El Niño of 1997 to 1998 proved even more remarkable. It became one of the strongest events ever recorded, generating months of powerful Pacific storms that drenched California, filled reservoirs across much of the West, and produced one of the wettest winters in decades. Floodwaters overwhelmed rivers and communities, while mountain snowpack reached extraordinary levels in many regions. More recently, the powerful El Niño of 2015 to 2016 generated enormous public attention. Many hoped it would completely erase California's historic drought. Although it produced significant precipitation and improved conditions in several areas, its impacts varied across the western United States. Some watersheds benefited substantially, while others received far less runoff than expected. These events revealed an important lesson. Even the most powerful El Niño cannot guarantee identical outcomes from one region to another. Storm tracks shift, temperatures vary, snow levels change, and the Colorado River basin responds differently depending on where, when, and how precipitation falls. Still, one fact remains undeniable. When the American West experiences an exceptionally wet winter, a Super El Niño is often among the leading suspects. It is one of the few natural climate events capable of delivering the widespread snowfall and runoff needed to produce meaningful gains in the Colorado River system. Which raises the question at the heart of this documentary. If a Super El Niño truly is nature's most powerful rainmaker, why haven't Lake Mead and Lake Powell already recovered? At first glance, the solution seems almost obvious. If drought emptied Lake Mead and Lake Powell, then extraordinary rain and snow should fill them again. After all, that is exactly what reservoirs were built to do. Capture water during wet years, store it for dry years. Simple, except the Colorado River is anything but simple. Long before a single drop of snowmelt reaches Lake Powell or Lake Mead, countless natural and human processes begin determining how much water will actually survive the journey. The first surprise is that not all precipitation is equally valuable. A winter storm that delivers rain to lower elevations may produce spectacular flooding, but much of that water rushes downstream within days. Some infiltrates into the ground, replenishing soils and aquifers. Some is absorbed by vegetation. Some evaporates almost immediately beneath the dry desert sun. Snow tells a very different story. When winter storms bury the Rocky Mountains beneath deep snowpack, the mountains become nature's largest temporary reservoir. Instead of flowing away all at once, the snow remains frozen for months, gradually melting through spring and early summer. That slow release is precisely what the Colorado River depends upon. For water managers, a cold winter with exceptional mountain snow can be far more valuable than a warmer winter producing even greater amounts of rain. But snowfall alone still does not guarantee full reservoirs. Once melting begins, the Colorado River enters one of the most carefully managed water systems in the world. Every major release is planned. Every reservoir level is monitored. Every decision balances competing priorities that stretch across 7 United States, multiple Native American tribes, and Mexico. Lake Powell, for example, cannot simply keep every gallon, or about 3.8 litres, that flows into it. Water must continue moving downstream to Lake Mead under long-established operating agreements. Hoover Dam must continue supplying water to downstream users. Cities continue drawing drinking water. Farmers continue irrigating millions of acres or millions of hectares of crops. Hydroelectric facilities continue generating electricity whenever reservoir elevations allow. Even during exceptionally wet years, the river never stops working. Then there is evaporation. The American Southwest is one of the hottest and driest regions in North America. Vast reservoir surfaces are exposed to intense sunlight, dry air, and persistent winds throughout much of the year. Together, Lake Mead and Lake Powell lose hundreds of thousands of acre-feet, or hundreds of thousands of approximately 1,233 cubic meter units of water annually through evaporation alone. That water never reaches a faucet. It never irrigates a field. It simply returns to the atmosphere. A warming climate adds another complication. Higher temperatures cause mountain snow to melt earlier in the season, often before peak water demand arrives downstream. At the same time, warmer soils absorb more moisture after long droughts, leaving less runoff available to enter rivers. Hydrologists have also observed declining runoff efficiency, meaning that a growing share of precipitation never becomes stream flow at all. In other words, the same amount of snow can now produce less usable water than it once did. Perhaps the clearest demonstration came during the extraordinary winter of 2022 to 2023. A relentless series of atmospheric rivers struck California and the western United States, producing one of the largest mountain snowpacks in decades. Rivers surged. Reservoirs across California filled rapidly. Flooding occurred in numerous communities, while satellite images showed vast expanses of snow blanketing the Sierra Nevada and the Rocky Mountains. For the Colorado River basin, the winter brought a remarkable increase in runoff. Lake Powell and Lake Mead both rose noticeably, offering welcome relief after years of decline. For the first time in years, many people wondered whether the long drought might finally be ending. But the celebration was short-lived. Although the gains were significant, neither reservoir came close to full capacity. Much of the improvement represented only a partial recovery from historically low levels. As subsequent dry conditions returned, a portion of those gains gradually disappeared. The remarkable winter of 2022 to 2023 demonstrated two truths at the same time. First, exceptional winters still matter enormously. They can stabilize the system, improve reservoir levels, increase hydropower generation, and provide valuable breathing room for water managers. But second, even one of the best snow years in decades was not enough to erase a storage deficit that had accumulated over more than 20 years. That realization changes everything. If one extraordinary winter cannot restore the reservoirs, if one of the strongest climate patterns on Earth cannot fully reverse decades of decline, then a much bigger question emerges. How many Super El Niños would it actually take? There is only one way to find out. Run the numbers. How many Super El Niños would it actually take to refill Lake Mead and Lake Powell? There is no official scientific formula that provides this answer. Every El Niño behaves differently. Every winter produces a different snowpack. Reservoir operations change from year to year, and no 2 decades experience the same climate. So, instead of searching for an exact answer, we built a simplified calculation using the best available historical evidence. Think of it as a back-of-the-envelope estimate, not a prediction of the future, but a way of understanding the enormous scale of the challenge. Our first step was surprisingly simple. Before estimating how much water a Super El Niño might contribute, we first needed to determine how much water was actually missing. Today, Lake Mead can store approximately 26 million acre-feet, or about 32.1 cubic kilometers, of water. Lake Powell, whose capacity has been slightly reduced by decades of sediment accumulation, can currently hold about 25.2 million acre-feet, or about 31.1 cubic kilometers. Combined, the 2 reservoirs have a total storage capacity of roughly 51 million acre-feet, or about 62.9 cubic kilometers. But by the summer of 2026, they were nowhere near full. Lake Powell contained approximately 5.6 million acre-feet, or about 6.9 cubic kilometers of water. Lake Mead held roughly 8 to 9 million acre-feet, or about 9.9 to 11.1 cubic kilometers. Together they stored only about 14 million acre-feet, or about 17.3 cubic kilometers. That means the system was missing approximately 37 million acre-feet, or about 45.6 cubic kilometers of water. 37 million acre-feet. It is almost impossible to visualize a number that large. 1 acre-foot, or about 1,233 cubic meters, is enough water to cover an acre, or about 0.4 hectares, of land 1 foot deep, or about 0.3 meters deep, or to supply roughly 2 to 3 average American households for an entire year. Now, multiply that by 37 million. That is the size of the storage deficit we are trying to replace. The next question was far more difficult. How much additional water can one truly exceptional Super El Niño actually contribute? To answer that, we turn to history. The great Super El Niño events of 1982 to 1983 and 1997 to 1998 produced extraordinary snowfall across much of the western United States and significantly increased runoff into the Colorado River system. Yet those remarkable winters also reminded us that not every drop remains in storage. Water continues flowing downstream, reservoirs must still meet operational requirements, and natural losses continue throughout the basin. Because every event is different, there is no universally accepted number. However, based on historical performance and using a generous simplified estimate, we assumed that one truly exceptional Super El Niño might produce somewhere between 3 and 5 million acre-feet, or about 3.7 to 6.2 cubic kilometers of additional net storage across the reservoir system after accounting for normal reservoir operations. At last, we had enough information to perform the calculation we had been building toward since the beginning of this documentary. If one Super El Niño contributed approximately 3 million acre-feet, or about 3.7 cubic kilometers of additional storage, replacing a deficit of 37 million acre-feet, or about 45.6 cubic kilometers, would require roughly 12 to 13 Super El Niños. if one extraordinary event contributed closer to 5 million acre-feet, or about 6.2 cubic kilometers. The same deficit could theoretically be replaced by approximately 7 to 8 Super El Niños. For the first time, we had an answer. Not one, not two, not even three. Under this highly simplified scenario, somewhere between 7 and 13 Super El Niños could theoretically replace today's storage deficit. It is a remarkable number. But before celebrating, we need to remember something important. Our calculation rests on a series of assumptions that simply do not exist in the real world. It assumes there are no droughts between Super El Niño events. It assumes water demand never increases. It assumes evaporation does not remove water from the reservoirs. It assumes required deliveries downstream never occur. And it assumes every Super El Niño delivers ideal snowfall directly into the upper Colorado River basin. Reality is far more complicated. Cities continue growing. Millions of people continue turning on their taps every day. Farmers continue irrigating millions of acres or millions of hectares of farmland. Water must still be released downstream to satisfy legal agreements, support agriculture, generate hydropower, sustain ecosystems, and meet international commitments with Mexico. Meanwhile, the hot, dry climate continues evaporating enormous quantities of water from both reservoirs, while rising temperatures reduce the percentage of mountain snowfall that ultimately becomes river runoff. Those losses continue every single year, whether an El Niño occurs or not. That means our calculation should not be viewed as a realistic recovery plan. Instead, it serves as a measure of the extraordinary scale of the challenge. In practice, even 10 Super El Niños spread across several decades might still fail to completely refill both reservoirs if water consumption, evaporation and warming continue at today's levels. That conclusion reflects the broader understanding shared by many scientists and water managers throughout the Colorado River basin. Long-term recovery is unlikely to come from a single climate event, or even several extraordinary ones. Instead, it will almost certainly require multiple wet years, healthy mountain snowpack, careful reservoir management, continued conservation, reduced water withdrawals, and favourable climate conditions working together. Perhaps no event illustrates this better than the remarkable winter of 2022 to 2023. One of the largest snowpacks in decades generated tremendous runoff into the Colorado River system and produced meaningful rises in both Lake Powell and Lake Mead. It demonstrated that exceptional winters still have the power to dramatically improve reservoir conditions, but it also revealed their limits. Despite one of the best winters in recent history, neither reservoir came close to full capacity. As drier conditions returned, part of those gains gradually disappeared. The lesson could not be clearer. Nature can provide extraordinary opportunities, but lasting recovery depends on far more than extraordinary weather. And that leaves us with one final question. If nature alone cannot fully restore Lake Mead and Lake Powell, what does the future of the Colorado River really look like? There is no single storm capable of restoring the Colorado River. Not one extraordinary winter, not one record-breaking snowpack, not even one of the strongest Super El Niños ever observed. As we discovered, the challenge facing Lake Mead and Lake Powell has been decades in the making. It was shaped by an expanding population, increasing water demand, a warming climate, and a river system asked to provide more water than nature consistently supplies. That also means recovery will not happen overnight. It will come through many wet winters instead of one. through healthy mountain snowpack accumulated over years rather than months. Through careful reservoir management, continued conservation, and difficult decisions about how a limited resource should be shared. Nature still has an extraordinary role to play. Future Super El Niños will almost certainly bring heavy snowfall to parts of the American West once again. Atmospheric rivers will return, rivers will rise, reservoirs will recover, at least for a time. But whether those opportunities become lasting progress depends on what happens after the storms have passed. The Colorado River has always been a river of extremes. Its future will be shaped not only by the forces of nature, but by the choices made by millions of people who depend upon it every single day. Perhaps that is the real answer to the question we asked at the beginning of this documentary. The future of Lake Mead and Lake Powell will never be determined by weather alone. It will be written by both nature and humanity, working against each other or together. And that story is still unfolding. Let's finish with one final calculation. Suppose, purely as a thought experiment, that Lake Powell received no new inflows from the Colorado River, no snowmelt, no rainfall, no tributaries. And imagine that its entire current storage was used for only one purpose, supplying large, water-cooled AI data centers. As of mid-2026, Lake Powell stores approximately 5.6 million acre-feet, or about 6.9 cubic kilometers, of water equal to about 1.82 trillion gallons, or about 6.9 trillion liters. Now, consider one of today's largest AI data centers. Using a generous upper-end estimate, assume it consumes 5 million gallons, or about 18.9 million liters, of water every day. Over 1 year, that equals approximately 1.83 billion gallons, or about 6.93 billion liters. Now, multiply that by 1,000. The result is about 1.83 trillion gallons per year, or about 6.93 trillion liters per year. That's essentially the same as Lake Powell's entire current storage. In other words, if there were no new water entering the reservoir, about 1,000 giant water-cooled AI data centers could theoretically consume a volume of water equal to Lake Powell's current storage in roughly 1 year. That's a remarkable number. But it also illustrates why this is only a thought experiment. In the real world, Lake Powell is constantly gaining water from snowmelt, while simultaneously releasing water downstream to cities, farms, tribal nations, hydropower facilities, ecosystems, and Mexico. No single industry receives the reservoir's entire supply. Thank you for watching.